Okay, so yeah, thank you, Alice, to the opportunity and this time here. Yesterday I was talking about essentially the application of mirror symmetry to a classical problem on algebraic geometry, and talking to people. After the talk, I noticed that I did a very bad job of communicating the punchline. So the punchline, for everybody who missed it yesterday, there are toric degenerations constructed by mirror symmetry that support families, okay? And that wasn't known before. So and today, it's a bit the other way around. So I want to show how to use methods of algebraic geometry to possibly go make a statement on the symplectic side of mirror symmetry, okay? So this typically, I mean, you know this from cohomology and so on, but in the high category, so far has been a little difficult to use algebraic geometric methods. So the motivation is use toric degeneration that you often have. In situations of mirror symmetry you're interested in. And what you're really interested in are is the general fiber of this degeneration indicated by some smooth object here. And then you degenerate and central fiber breaks into the union of toric varieties. And that is the situation that you can capture with tropical data, discrete data, B, this manifold here, and P, the poly-B composition that you see. I mean, this is like a real picture of what's going on with the central fiber, using also momentum polytopes. And then you can produce canonical polarized such families, typical of high-dimensional basis, like yesterday, by some smoothing algorithm, involving Moore crossing, scattering dynamics, and all this stuff. And with my pipe tree, my personal obsession, one of my mathematical personal obsessions, was to describe the Fourier category in terms of certain algebraic curve counts on the central fiber. Sounds a little nuts, but I'll show you what I mean. And today I will take some steps in this direction by looking at the easiest non-trivial example, the K curve. It's a degeneration of the elliptic curve. But before doing that, let me remind you of some slightly older story. Tropical Morse category work, some ideas in joint work with Mohammed and Mark in 2007 already, and Mark wrote this down in the playbook with several, quite some extended work, to work this picture out for the elliptic curve for degeneration. So what is this? It's a typical, purely cohomology object, if you want, F1 geometry object, tropical Morse category. The objects are just the integers. And you should think of these as powers of the ample line bundle in the Dirac category, or on the mirror side, a slope of a Lagrangian section. So think of something, we will work on the elliptic curve, so that the base would be an S1. You take here the tangent bundle of S1 as an integral affine manifold, and divide out the integral lattice. It becomes an S1 bundle, and then you have canonical Lagrangian, I mean, it's really not Lagrangian, but let's call them Lagrangian sections, canonical sections of a certain slope. So L0 is just a zero section, and then you can go like, you travel as much as your distance tells you, that gives L1, and if you travel twice as much, it gives L2, and if you travel this minus the distance, it gives L minus 2. And then the home spaces are very simple. These are the section spaces of Li and Lj, and you can see, like here indicated in the picture, let's say I take Li to be L1, or maybe, yeah, let's take L1 and L minus 2 is Lj, then you would get as a 1/3 rational points. So everything is denominator 3. So here you see the first intersection point of L minus with L1, and then the next one would be here. That's the 1/3 point. So that's it. That's the objects in the home spaces, and then the point, of course, is to define the structure coefficients. And they are done by what we call tropical Morse trees. And that's first some explanation. So you should think of these tropical Morse trees as kind of piecewise linear versions of an ordinary Morse tree, where you start with these Riemannian manifold, your functions, you take the differences of the function and look at the gradient flows. These are critical points of the differences of the functions. And we will have something similar. So it will look like this. You have some tree on your, this is a picture on B. And it had leaves indicated by these points. These are elements of the home space. So these are these rational points with a certain label I minus j on your B. And these are the analogs of the critical point. And that's where you start your kind of gradient flow. And then if you have a 1 over d rational point, you start here with speed 0, and then you start accelerating this d. Yeah? Because you think of this as, well, no, let me not make this on the next slide. So let's just describe what it is. So you start here with speed 0, and then you go faster and faster, okay? And the d tells you how much bigger you go as you travel. And then if two or more such edges meet, you have a balancing condition as the tangent vectors that are carried along. Okay, so it's different from these tropical curves. So first, the slopes can be arbitrary; they are not rational or anything. Yeah, S are these vectors that are carried along, and they go continuously. Okay. Then it can happen. There's also a sign, right? So label I minus j can be positive. So that's a picture. You would everything would be positive. But if it's less than 0, it means there's a negative acceleration, a deceleration. But you cannot decelerate something that is already at speed 0. You don't go in the other direction. This just sits there, and that would just mean that the edge that is adjacent to your point, this vertex that is giving the leaf. This kind of leaf would be contracted. So there could be crosses directly on the curve, but that means it's just something that would attach with kind of speed 0, length 0. And then this, in generality, I mean, if you do this in general pictures and higher dimensions, you would have wall structures that these lines here cross, and then they could bend. But this will be entirely irrelevant for the elliptic curve. There's no such bending.
So mostly this the one that starts on the critical point is straight, but this one in the middle is actually curved.
No, these are straight. They are straight, but they are not rational.
Yeah, I mean, if you just go the gradient line of most times.
Yeah.
Then this middle one is actually curved, but you just define to be straight.
Yes. Everything is straight. Exactly. So this is a slightly intimidating slide, I think. So let's go through this slowly. So there's a 1-1 correspondence between tropical Morse trees and certain polygons, and that's really the motivation for this our definition. It's just a kind of discrete way of writing down these polygons in the elliptic curve, bounded by these Lagrangian sections that are really just these lines wrapping around your torus. So I'm trying to draw a ribbon graph here, conveniently embedded into some disk. And these purple things here, they are, well, these are the LIs, I mean the index I, right? So if 1 means that this part you should think of ending up on your, of attaching, I mean rather this boundary edge here, right? Attaching to L1, this would attach to L3 and so on, right? So this point, this intersection point, go for L1 and L3 and so on. This here is a tropical Morse tree. Of course, it's a little hard to draw tropical Morse trees on an S1 because typically we'll travel back and forth. Yeah, so this thing here is really, you should project it to an interval that wrap around. So you see here it's P2, 3 would start somewhere, so that's an intersection point of 1 and 3. So that means 3 minus 1 is 2. You start with speed 2. And then you travel, and then at P3, 4, it changes the speed to -5, -3, which is, what is this? Something's wrong, huh? No, wait, this is the, I'm confused. No, that's the 6, no, that's the 5W, sorry. Then it goes here, this is this thing. That's a -5, -1, that's a -6. Right. So So at P3, 4, exactly, that's a negative thing, right? Minus 5 minus 3 is minus 8. So that is actually one of those contracted edges that I was talking about. So here is just a zero length edge attached to it, and so on. Now you can translate this into a polygon where you just shape the kind of, so these will, they will just, I mean, let's just start at some point, yeah? So this thing would be the T12 actually, okay? So then it tells you that on one side you have a boundary on L1, and on the other on L minus 2. So the slopes here are a little, there's some sign convention that makes these slope look like slope minus 2 rather than 2, but never mind. So this is slope 2, this is slope minus 1, and then the rate of increase of area is 3, right? And that's the 3 you see here, okay? And then you can continue, and sometimes there are these funny pictures where you actually, this kind of degenerate polygon, so there's an edge that actually comes back. Yeah, so that can happen. But in any case, there are these, this is one non-correspondence. So that was the motivation for this tropical Morse category. That is a little cumbersome to work with, and there's the various technical problems that made us believe that this is maybe not the best way to approach the Foucault category in our picture. But who knows? Maybe at some point we'll take this up again. But there's an easy trick that will translate these tropical Morse trees into ordinary tropical curves. Things I think most of us are familiar to work with. It goes as follows. So you take the affine cone over B. Okay, that means this is a picture of B, just unwrapped. It's an interval or maybe even a real line. And you take the cone over it. So this sits at height 1 in R2. And you just take well, in this case it's the upper half take, right? It's a cone of it. And then I will do this on the next page. So what will happen is, if you draw a tropical curve here, and you project it along the radial directions, it will project to a tropical Morse tree. So the tropical tree in this cone, in this big thing, will translate into a tropical tree. So how comes it that we, for example, start with speed 0? Well, if you think of something going off to the upper to the top, well, you see that if you follow it, the asymptotic direction is like this. Yeah, so you would end up with this point. That's your end point. But if you travel along this constant speed here, it means that the projection will go slower and slower as you approach this point. And then once you reach the point, the speed is 0. Okay, that's how you should think of it. So, unlike tropical Morse, okay, so these terms of tropical Morse have been truncated. Yeah, we truncate here, but otherwise ordinary tropical curve, and we call it a tropical coral. I'm not sure if you have a better suggestion for a name, but it looks a bit like this kind of coral-like thing. Unlike tropical Morse trees, the edges have no piecewise rational slopes. The usual thing, this piecewise constant integral velocity vectors. And by the way, the projection of the speed of this velocity vector to the height, yeah, to the right, that tells you this multiplicity, the acceleration. That's the acceleration, the d that we had before. Okay. So this has two ends. We have positive ends, I just discussed, and they are giving the points, your end points give you the asymptotic directions, like indicated here, or like this one would be this asymptotic direction, and so on, right? But you could parallel transport, and they would have the same, project to the same kind of, or tend to the same endpoint. And then we have negative ends. These are the things that attach to the lower boundary, to this thing. Okay? And here we want that the tropical coral actually ends at the point that you want to end at. Okay? So there's no parallel transport possible. And then again, with the non-trivial wall structure, you would take the cones over the walls, and then you have the things that we call broken lines that came up in our construction of theta functions. Okay, so I'll try to draw this a little bigger here. So this was our rim graph. And then let's just go through one thing here. Let's take this one, that is P01. So that was -2, -0. That's a -2 slope. So it's a negative end. That's why I have to attach it here. And it happened to have endpoint at 8. And then I have no choice and travel in this direction. So we have also some orientation. You could add an arrow here, goes in here. And then it attaches to something for a positive end, that would be the P12. That's a 1 minus -2 equals 3. And this one is parallel to, where is it, this one? And you see here is the velocity vector. It's -36, -3. The second entry is what I told you is the acceleration. Yeah? So that works also fine. And here comes the challenge on the symplectic side. So in tropical geometry, you can just make this simple observation. Something extremely simple. But what does this mean on the symplectic side? Tropical curves have something to do with, holomorphic curves, okay? While these tropical Morse trees had to do something with disks, with boundaries on Lagrangians. So going over to this cone on the complex side, that means actually the total space of the ample line bundle. Well, in this case, these broken lines indeed were used for these construction of theta functions, because functions on the total space of the actually inverse ample line bundle, these are sections of the line bundle. Okay, that's elementary algebraic geometry. The labeling set is as expected. But we are interested on the symplectic side. In this space, this truncated cone, C bar B, it describes the total space of the mirror degeneration. So it's one dimension higher. You start with xt, and you write down the thing that describes the total space of the mirror degeneration. So taking literally in our picture, that is something you will have to study. You take a degeneration of the total space of the degeneration. A toric degeneration of a toric degeneration. It's a two-parameter thing. And this correspondence tells you that we should look at tropicalizations of holomorphic curves in the total space of the mirror. Okay, so that comes very close to my pipe dream to describe the Foucault category in terms of something algebraic geometric. So it suggests to describe the Foucault category of the general fiber, the thing we're really interested in terms of certain holomorphic curves in the total space of a toric degeneration.
So what corresponds to this Lagrangian Summary code?
Sorry, say again?
What corresponds to this Lagrangian Summary code in this picture?
You'll get to that. Okay, so that's an interesting thing. It will be a periodic orbit of Hamilton. Okay, so this suggests a description of, and then Mohammed in 2012 I told him of my pipe dream and this observation, and he suggested, well, you should maybe look at the symplectic cohomology of the complement of the central fiber. It's a non-compact symplectic manifold with two ends. And then he told me many stories on how all these objects should be related, the Foucault category of the general fiber, the red Floer theory of the complement of the central fiber, the symplectic cohomology of the complement of the central fiber. And maybe I've still not quite made up my mind where my favorite place to work is. Okay? So, and we'll make a little bit of an attempt of going here. Okay, so now let's focus on the tape curve. I was long reluctant to look at the tape curve. It just seemed a bit too simple. I mean, the elliptic curve, come on. We all know how to do the elliptic curve. But then it was last year only that Mohammed kind of convinced me that maybe it's actually the place to start. After having not had much progress on this for some time, so I asked my student Julia Argus to look into this, and what's following is John Burke's curve. So this example has no walls, an elliptic curve. So how do we do this? So it's the tape curve. Is this degeneration of an elliptic curve? The general fiber is just a quotient of elliptic curve written as a quotient of c star mod u, and u is this complex parameter on a unit disk. Okay, if u takes value 1, it's a very good space. As well as that's the value of u is less than 1, you get an elliptic curve. And if you tend to u equals 0, something is happening, and you can fill in this nodal elliptic curve. And well, in general, you could have more kind of this rational curve with 2 points attached. You could have a whole cycle of things, depending on how you do it. What you do is, to construct this, is a purely toric construction. You take this infinite fan, and then each of these lines give you some, so it gives a certain degeneration, has a map of fans to this upper line. And that the toric variety here is actually trivial. It's a trivial product of C star with C star, and then you fill in a central fiber, kind of infinite log of C star plus C, that gives an infinite chain of P1s. And then that works algebraic geometrically, that's over the whole complex line. But then to take the quotient by Z, you have to restrict to absolute value U less than 1, and that quotient only works complex analytically, and that's how you arrive at this thing. So that's a tape curve. Okay, so now I want to do a toric degeneration of a toric degeneration. Okay, so I'm taking my picture I had here. Sorry, where is it here? Or here, whatever you prefer. Takes this thing here, that's the kind of real line with all these intervals where it takes that defines the fan. And I view this as a picture defining a toric degeneration. So now I have to take the cone over the thing to get something three-dimensional, and then view it as a fan and takes its corresponding toric variety and do the whole thing. Okay? What this gives this process of taking cones, if you analyze it, it's this very simple operation in algebraic geometry. It will just do a base change. So you just replace the parameter u you had before, C star mod u, by s times t. Okay, so your new base is two-dimensional. There's two parameters s and t, and s times t is u. So if you take a slice for t constant, yeah, so let's say for t equal 1, you just get the usual curve back. Yeah? So just the usual curve. But then as t goes to 0, you rescale the thing. Yeah? So you look at the tape curve and don't look at the unit disk, but you rescale it and zoom closer and closer into the origin. Okay? So for any constant t, it's just a tape curve in a slightly different coordinate, written in a slightly different coordinate. And then at t equal, for t to 0, we zoom into the origin until at t equals 0, you get just a trivial product of the central fiber with the complex line. Okay, so that is will be just a normal elliptic curve across the affine line. Something perfectly algebraic geometric again. So here I've written down this domain of definition of this family analytically. Okay, so that's the central fiber. Let's say now B, the number of nodes, number of P1s, rational curves in the central fiber was 5. And this is just these 5 P1s, a cycle of 5 P1s cross C. Okay, so there's still a central fiber. S is now our new parameter. S equals 0, but it doesn't really look any different from the S1 0. There is still something that records you that this is not just a product, but that's hidden in the log structure that I will not tell you exactly. So and then this tradition, the transition tropical to holomorphic that we will do first, as a first step, that's not something completely algebraic geometric. Okay? This is a perfectly algebraic geometric object, nothing analytic. You can define the thing, no problem. Then you observe that all your tropical corals will only hit finally many of these cones that you these cells in your fan, the cones in your fan. So you can just forget everything else and undo the z quotient, just to work on the central fiber first. So let's do that. So right, this x0 tilde is still a z quotient of some. Now here's a toric variety. Okay, it's just a toric variety corresponding to this kind of the cone over this kind of thing. The fan that would take the cone over this in R3. Okay? So, and I'm just observing that these tropical corals, we're doing genus 0 stuff, are simply connected as are our rational curves, so you can lift both on the geometric side and on the tropical geometry side to this z quotient. Okay, so and then let's just take this thing. So we are first looking at this very simple thing. Yeah? So you take a chain of P1s, find the many, cross C. This is Y0. Now, this is almost what I know how to do a long time. With Takio Nishino in 2004 wrote a paper on toric degenerations of toric varieties in tropical curves, and we looked at exactly the situation where you want to count curves, rational curves, in a toric degeneration of a toric variety. There's one crucial difference, and this is actually something that confused me maybe for a long time. It still kind of confused me at one point. So maybe one punchline of this part, and won't forget this time to make it. So it has a lower boundary. Yeah? So usually toric varieties, in complete toric varieties, you would have a polynomial decomposition of a whole Rn. But now we only have a subset of Rn, maybe something like the upper half plane. Or maybe even only an open subset of the upper half plane. And you see there's a problem in the count, right? The count will depend on where you fix your asymptotic, these unbounded edges. And if you move them too far, if you force them to lie too far down, there's some vertices vanishing under your horizon. You can't see them anymore, and the curve becomes disconnected. So that indicates there should be some problem with compactness in the deformation process. Okay? And certainly also in the tropical counting problem, because that looks a bit strange. You don't want to count this stuff. That's a good thing. This is something strange. So the first thing we define is what we call stable range. It's rather obvious. You want to kind of fix your incidence conditions sufficiently high up. So if you well, let's go down on the page here. So there's first the dimension count. You fix or maybe start here, the degree of a tropical coral. Well, what is this? The degree is the asymptotic directions. Yeah, so we have positive ends. That's n plus asymptotic directions, delta upper. And then n negative ends, these points on the lower boundaries that you fix. And that's the delta lower. Okay? And they are both determined by certain reference points on B. Okay? And that's what I fix. Okay? That's like the degree of the curve. You want to count something like degree 3 curves in P2, we would also fix something. Now we count something a little more difficult, and there's a degree. And then there's a dimension count, namely you have to, the negative ends are fixed, there's nothing to be labeled, right? They just sit there. But the positive ends, as I showed you in this picture, right? They can be parallel transported. And I have to fix some condition at infinity. So I tell you essentially, where I fix this asymptotic line, affine line. And that tells you that the dimension count works also with n plus positive and n minus negative is you have n plus minus 1 dimensional space. But that holds only if you're not in the lower range. So if all your vertices that you care for are above your horizon. And if that's the case, we call this a stable range. And you can always get into the stable range if you just rescale. Yeah? So think of this and apply a uniform stretch by, I don't know, maybe 2 or something, and that point will end up here, and everything is in order. Okay? So that just means that's a certain. The good thing is this rescaling will have a good interpretation on the algebraic geometry side. It's just a base change. Okay? It's a base change T as the T will be. Okay, then we have a tropical coral count, just as in, it's just purely tropically. It's essentially a Mikalkan multiplicity sum. The sum of all tropical corals is fixed degree and fixed incidence conditions fulfilling certain incidence conditions, and then the sum of the multiplicity defined by Mikalkan. And then there's one overall factor that you have to divide out that takes care of the geometry at infinity. It's the weights of the unbounded edges. Only the positive edges. Okay, now let's go. So let's talk to geometry. The tropical story ends here. Nothing more we can do. Okay. Now we have to go to geometry and look at what the analog is in logarithmic geometry. So on the central fiber. So now in our program, we often first construct something on the central fiber with a little bit of extra magic powder, which is this log structure, that makes makes it possible to actually extend everything to nearby fibers. So of course I'm not going to tell you, bore you along, I mean this is log structure stuff, but here's the definition. So I want to analyze, well, we have this procedure that tells you that if you have stable maps together with the magic powder, the log structure, there's a way to extract canonically a tropical curve. Okay, so let's take this as a blackboards. And many years of experience with Mark on how to do that. So I can just understand what it would mean to write down a logarithmic thing that would produce a log call. And it's essentially the same definition you would do for a stable logarithmic map, except the only difference is, so that something over what's called a standard log point, like a kind of infinitesimal one parameter thing. That's this n here, the t parameter, t, actually maybe I should, yeah, the t to b, tells you the one parameter degeneration. That would be your central fiber with the log structure, also viewed as a one parameter degeneration space. Anyway, the only difference really to the standard case I did already with Taki and Nishino is that we have non-compact components, okay, necessarily. I mean, our space is this kind of mode curve cross C, and we do see this non-compact component, so there will be components going off to infinity. I will draw some pictures very soon. And I assume that they should be genus 0, so I assume they are just copies of C attached at one point to the other points, unless I to get genus 0. And they should project properly to the S-plane. Yeah? So let's try to look at this. So this is a geometric picture, that's a tropical picture. This is this 3p1s cross C. I have one non-compact component, that's a copy of C, that is just the straight product of this P1 cross C, attached to one P1 that just covers this P1 isomorphically. And then there are also two marked points. The marked points, they correspond to these unbounded edges. Unbounded edges give marked points on the central fiber. Okay, while the negative ends, they will give these unbounded edges, I mean these non-compact things, these C components. Okay, so I have two marked points, and then we could have a tropicalization that looks like this. You should think dual intersection graph. So your intersection complex, this kind of thing, this component is actually this dot down here. Okay? This is like the fan of this. If you look at the fan, it's non-complete. It's the fan of P1 cross C. That's this P1 cross C. So this component is this dot. So then you have one node connecting it to the next vertex. The next vertex is the irreducible component that's contracted, that is this thing here, and goes to the central fiber. Central fiber means the vertex is above the lower horizontal line, the lower horizon. And being on the thing means it actually maps to the component. It is not contracted, yeah, because this edge here, this is dual to this component on the central fiber. And then these two incidence conditions, they have certain vanishing kind of attaching orders. And the attaching orders that you cannot see from the picture but would be hidden in the log structure, there would be some unbounded edges going off like this. And of course you see tropically that's non-generic. Yeah, that's a very special position. I mean this point is here, this point is here. And if you fix these incidence conditions, I mean generically you would move this away. Yeah? And then you would end up with something something like actually no, this has to fix. This has to stay fixed, but actually no, there's nothing I can do here. I can only move it up or down actually. But it interacts with the polymer decomposition, and generically you would not necessarily assume this. Okay, the next picture, tropical or more generic. It's this tropical picture, and then you see it gets into a more special position in the geometry side. So here you have two vertices in the interior of these lower edges, and they mean they cover these double loci. Okay, and then here are points in the interior of these big cells. They would be contracted components over these nodes. And then there's there are two components Did I draw this correctly? No, sorry, there's one component, I did draw it correctly. So here, two more components that are contracted. They have two marked points, this one and that one. And there's another one component that would pop up. So this is about how it works. In practice, of course, you don't actually have to do this just for illustration. Okay, so now what was a stable range property? That was a little puzzling. So we have to have some kind of analog of the stable range property, and this is actually already indicated in these pictures. That would be a nice picture where this is not going off. Yeah, so what you could also have, of course, is something like this. Yeah, some curves that would just happen to end up here, but not like in this direction. And if you analyze it, what this means is, or maybe even have this kind of thing. Yeah, it would mean that you can exclude this by asking that your curve is just a product. It's not some more interesting curve in here. There are many other curves. You can take something like a section that kind of looks here, it goes over and has this one point here. So that is the meaning of being stable range. So we asked for definition that the unbounded components, the definition asks that the unbounded components are constant in the x0 direction. Yeah? So there's a projection of our x0 tilde to x0, the center fiber, this union of p1s, and these unbounded components should just be products. Precise definition has to be a little bit careful with the components that go to the double locus, but let's ignore this here, okay? There's a statement that makes it kind of compatible with blowing up the whole process, introducing more components. Then you would make sure that it would still stay asymptotically parallel. Okay, and then we impose incidence conditions at infinity. Okay, this is just a kind of projection to the x0 direction. Now, what does this mean? So I said we can rescale the thing that would make any tropical coral get into the stable range. What does this mean in geometry? So there's also something we know for a long time. Let's look at the model picture. Let's take P2. Think of a momentum image here that I'm drawing, and let's try to count lines through 2 points, and the 2 points happen to be on the divisors. But the first point, well, you know that's a nice tropical counting problem, and the corresponding tropical curve would just be the kind of curve in terms of dual intersection graphs that is the one skeleton of the fan of P2. But I can now look in tropical, I can now degenerate this incident condition. Let's say, give it a parameter t, and really look at the thing in P2 cross A1, yeah, and degenerate these incidence condition at speed t to k or t to l. Then what is the tropicalization I'm getting? What I'm getting is a shifted tropical curve, a shifted tropical line. It's a distance here is k, the distance here is l. So what this is saying is that doing a stable range property does something with the incidence conditions on the center fiber. Okay? The moment we look at the degeneration of the tape curve, let's go back to the proper tape curve for t non-zero, you would impose certain incidence conditions. So if this is your tape curve, that's supposed to be some kind of smooth fiber. You would have some incidence conditions on the central fiber. Yeah? What this is saying is you have to degenerate these incidence conditions sufficiently quickly to the next node. Okay, that's a very odd condition. One puzzle in the problem why this is a good condition. Okay, puzzle on the symplectic side. I'll get to that. Okay, so it becomes only this counting problem, the logarithmic counting problem, becomes well defined once I impose this kind of condition. Once I take the corresponding incidence conditions sufficiently degenerate, then it's a good counting problem from the point of view of logarithmic geometry. Okay, then here's the main statement. We have a log counting problem. So if you choose these incidence conditions in the same range, the log of count of log parts is well defined. each log coral is unobstructed, so it just counts 1, and well, the log corals count 1 exactly, and then we have the correspondence equality between the logarithmic and the tropical counts, just as in ordinary probability. Maybe there's one observation. We don't really use these unbounded components. You can just get rid of them and have the same information. I mean, we have a finite list of these logarithmic corals, these logarithmic stable maps, and they have just these silly components that don't contain any information really. I could actually get rid of these, just remove them, at the expense of introducing. So you would kind of remove this. So there's something else coming in here. And now you remove this point, this component, and you end up with a point here. This point is not a marked point. It's what we call a puncture. So this is some notion under investigation in joint work with Dan Abramovich, Chile Chen, and Mark to define these punctured Gromov-Witten invariants. Okay, and that's in the making. And what I want to say here is that the count we are doing here, these log corals, is actually punctured Gromov-Witten count on x0. Okay, so if you don't like the degeneration, it's really something that works entirely on x0. Okay. Okay, so that leaves us with the interpretation of tropical Morse trees and this Gromov-Witten invariance of this whole space of the degeneration. And now you could just say, why do I care? I mean, if I just want the Foucault category, some definition of the Foucault category, let's just take it. Yeah, so let's just develop a theory, a Foucault category, some A infinity category, in terms using log corals as structure. Use counts of log corals as structure coefficients in your N infinity structure. And I believe that will work. Okay? So hopefully it will be worked out at some point. But then maybe I'm still too much a symplectic geometry but to not care about the symplectic side. And I think one of course wants to make contact to the symplectic side. And go back to Mohammed's proposal and show that our log corals indeed compute, well, higher structures on symplectic cohomology. Yeah, so the silly structure would be this kind of log coral that's just a line. Yeah, so you could take for any point there's one unique line through the origin. It's like defines the differential in pairing the negative and the positive end with a kind of differential. But everything else, these more interesting corals will be of higher structures. Okay, so let's try to see if our counts have anything to do with symplectic cohomology. So, as a reminder for myself, here's a slide of what symplectic cohomology is. That's a theory, a cohomology theory, some kind of Floer theory for symplectic manifolds with cylindrical ends. Where the cylindrical end looks like a product of a contact manifold N with R. And then the construction depends on the choice of a Hamiltonian with slope going to infinity, with gradient going to infinity near the ends. Hopefully, the construction depends, but hopefully not the result. But that's a challenge. Okay, that's typically it's hard to show, and one has to be very careful to make this work. From what I learned in looking at the literature. So the generators of symplectic cohomology are time 1 periodic orbits of this Hamiltonian. And then near the ends, you can find out that these are in projection with closed orbits of the red vector field of your contact manifolds, but of any period. So in symplectic cohomology, you just look at time 1 periodic stuff, and then kind of you capture all the periodic orbits of your contact manifold. And then the differentials are computed from cylindrical solutions of the Floer equation, so that involves here the Hamiltonian vector field, and hence implicitly the symplectic structure. And towards the end, plus or minus infinity, you tend to a time 1 periodic orbit of H, so it's like this picture. These are the time 1 periodic orbits of plus x minus that you would fix. Unfortunately, the situation you're interested in is not very well covered in the literature. And I think that these are the only two cases that come kind of close to what you would need. There's some early work, somewhat older work by Oliver Fabert, his PhD thesis with Chili work 2006 about Hamiltonian mapping tori. Well, first observe that the tape curve, if you remove the center fiber, is topologically a mapping torus for the Dehn twist. So you want a Dehn twist on an elliptic curve, you can cross an interval, and then divide out the symplectics, glue the two ends with the symplectomorphism, and then take cross arc. Okay, that is what it is topologically. Oliver was looking at a case where this symplectomorphism was a Hamiltonian symplectomorphism. Of course, the Dehn twist is not Hamiltonian, so that is not really the case we have. In this case, he found out that that symplectic cohomology computes Floer homology of all powers phi to t. And yeah, the other case that is maybe closer to what we are looking for, but still not quite the same, is a recent work by James Pascalev on non-colloidal surfaces. So related to the story I told you yesterday, it was this work of Ross-Hacking and Kiel. So there you start with a surface, compact surface, with a cycle of P1s that is anti-canonical. So these is a log colloidal. And then there's this singular dual intersection complex that would glue in some integral rational polynomial cone for each vertex in terms of the intersection number. I mean, that's a standard thing, actually. So there's normal crossings. So it's non-singular, right? It's a normal crossing thing. So this is just a copy of n squared. R maybe if you want, yeah? N squared, standard cone. And then again, I told you yesterday, the F, you can define an affine structure depending on the self-intersection number of the irreducible components. So that glues together to some fan. The affine structure does not embed in Rn because you have a singular point here. But for this statement, you don't care. What James proved is that you find a basis of the zero-graded part of symplectic cohomology that is labeled by the integral points of this fan. Okay, so there's an n squared worth of integral points for each such cone. And so how do they come about? Well, it's based on an analysis of taking a little torus bundle over your strata. So it's an idea going back to Paul Seidel, I think, that you find in his biased view in symplectic cohomology, sketched how to get hands on the web dynamic, or this Hamiltonian dynamic near this end, near the boundary, in terms of circle actions. So in analyzing this carefully, James managed to show that the corresponding generators of symplectic cohomology are either, well, think of a real blow-up of the thing, yeah? So you would find a two torus over these points, and then a product of C star with S1 over these things, over the edges, these interiors of D, so the components, reducible components of the divisor, anti-canonical divisor. And there's just, I mean, here you can just wrap around just an integer. Well, these correspond, again, dual intersection complex, they just correspond to the integral points on these blue lines. Yeah? They are dual to these things. And otherwise, an integral point here would tell you some kind of multiply wrapped thing in a torus, closed curve in a torus. And these are the generators. Okay? So that kind of indicates that what we should be looking for, again, well, we have integral points, we have some kind of fan, And so we should look at something that is some kind of rep dynamics near the central fiber. So there are a couple of challenges here. The first challenge is it starts at the very beginning. Yeah? Symplectic cohomology depends on the choice of the symplectic form, not just the class. So I don't even know what the right thing is to work with here. There are many things I could think of. There's a natural structure on the Tate curve, Taylor form, coming from embedding the whole thing into P2. Actually used by Tim Carrots, Tim and in his work with Yanko on the Tate curve. But there's also a Ritchie flat one, Ritchie flat metric. Probably hard to get your hands on, but there is, and then actually one can. There are formulas, but a little complicated. You could also think of defining some kind of asymptotic contact manifold for the radius going to 0, and then taking a syncretization of it. It's different from the other two. Or you could take your favorite realization of the gain twist as a symplectomorphism of the torus, and takes a symplectic mapping torus, like Oliver Faber did. Hopefully this choice is not so relevant, okay? But whatever you write down explicitly will depend on your choices. Second thing is we need a natural kind of Hamiltonian. So after discussions with Mohammed and thinking more about it, I think natural choice would be a convex, or maybe concave function, depending on your terminology, Hamiltonian, depending only on the radius, distance from your, in the usual polar coordinates on your disk, on your unit disk. And then the derivative has to blow up once you approach the central fiber, and it has to decay to 0 once you go to the boundary. So that will focus the whole geometry, the whole interest in geometry to the central fiber. And remember, our logarithmic curves, the only information we really capture is on x0. So I don't believe anything is happening at the outer boundary. It will all be things that happen in arbitrarily small neighborhoods of x0. Okay, so once this is set up, and you believe you have the right setup, there are the real challenges. We have to deform our log codes uniquely to the solutions of the Floer equation. Okay, so here's some sketch on how this might work. Might all be nuts, but that is some way I could believe things could fit together. I'm not comfortable in doing log deformation theory directly with the Floer equation. I mean, that will be, I think, very messy. What I'm happy to do is doing log deformation theory in the analytic context. That's essentially standard. And, but still, there's a problem because we're non-compact, or at least we need to deform to something really analytic, having something like look at the topology of a disk or a cylinder. So you have to specify, restrict where your outer boundary goes to some kind of. You have to fix something on your outer boundary, okay? So I first want to use this kind of log deformation theory, log holomorphic deformation theory, to deform your log curl to something non-compact with some boundaries. I mean, some sphere with a bunch of disks removed for a small t. Okay. So critical, we have to replace these non-compact components by certain disks forming small circles around x0, like these generators that Pascal wrote down. So then there is, hopefully, and you have to make the step to get from something holomorphic to something Floer theoretic. And I think there should be some kind of wrapping trick to transform holomorphic curves to something close or even equal, depending on your choice, precise setup. Solution of Floer's equation. So I found some stuff in a rather refined fashion in work of Luis Biorgo. Use it in a different context, but he has a really one-one correspondence between things entirely holomorphic or J-holomorphic and something involving a Hamiltonian function. So If it's not directly equal, then hopefully you're sufficiently close to it to use an implicit function theorem to actually get to some solution to the equation. Okay, but then you're still not done. Then you know, okay, you get something, but you have to show that you get everything. So then you have to be careful to establish compactness. But hopefully would be a standard argument. So here's an honest question: where really does the stable range property enter? This kind of funny thing where I told you, where is it? That the log counting prescribes you to have your kind of rep orbits that you would now think being attached for t non-zero really at this point. A small circle going around the thing. But it has to converge sufficiently quickly to this double point. Okay, that must come in somewhere. And my guess would be, the only place I can imagine is that it has to do with the compactness argument. Might already have to do with this thing, but anyway, so that's a challenge. I don't know. So that's about my last slide. I sketched the example of the tape degeneration of elliptic curves. How log probability techniques may be used for an algebraic geometric definition of the Fukaya category. But to make context with symplectic geometry, subtle problems, the last two slides, remain to relate log choral counts, which is something entirely on x0, something degenerate, to symplectic homology. But these may be solvable. Maybe this whole approach of symplectic homology is still not so good. You may also think, I told you on like second or third slides, that I'm still not entirely sure where I should put my finger, where I put most effort. There's still another candidate, which is the Rad-Fukaya category. And there's another fantasy using the Rad-Fukaya category in a purely algebraic geometric fashion, which would use a real structure. So there's some distinguished non-compact Lagrangian, which is a positive real locus. It lives over the positive real line, or a half line, over the disk. Well, hard to draw. Of course, there's a main twist, but it would live over this thing here. So there's a family of these elliptic curves and lives over this guy. So there's such a Lagrangian. But then, of course, still for the Rad-Fukaya, you would still employ, it has the same kind of problems. You would need to devise some symplectic structure, some Hamiltonian, and so on. And one thing I've been advertising to symplectic geometers already for some time, I think. Not sure if my suggestions have been heard so far. I believe, and maybe in the work of Nick Sheridan, that already appears in some way, that this symplectic monodromy transformation that you have near maximal degeneration point is a very important information in the mirror symmetry story. It's a kind of symplectic analog of something like tensoring with the ample line bundle. So it's not, I think mirror symmetry should really not just be a symplectic manifold, but it should be a symplectic manifold together with this kind of maximally degenerating structure. Kind of generates a Fukaya category from an SYZ section once you know this kind of transformation. Okay, so this is about what I wanted to tell you, and I'm happy to receive any suggestions from the symplectic community how to proceed. Okay, thank you.
Questions? So do you see the infinity of Floer and why changes satisfy the infinity equations in your picture?
Yeah, I think so. Yeah, right. Symplectic homology has an infinity structure.
But symplectic homology is more commutative.
They are not what?
Symplectic homology is more commutative than say each identity structure. But
right.
You said you symplectic
Well, right. There's maybe. I know we should talk a little about this. There's some confusion I have actually. For the Fukaya category, you would really split your sphere in as a real structure. Right? I would just use that I have got given real structure on my picture operating. I do something like real log chromosome theory. Another joint work with Julia, by the way, and there's and that would break the thing into two disks, and there it would come from. Yeah, I don't know how to really get the anything structure on this level at the moment, or the one one really wants.
So I repeat my question. I understand that the symplectic cohomology is related to this kind of pictures, but how this Lagrangian manifold is transformed in this picture?
How the Lagrangian is transformed? What do you mean transformed?
I mean, if you don't want to calculate almost this kind of things, you have Lagrangian manifold, things, and on these pictures.
Yes.
So I don't. So what is the? How
well, you go from L0 to L1, right? I mean, if you wrap around, you turn L0 to L1.
So you go to the pair of Lagrangian manifold, which is the kind of transformed by something.
No, I'm taking if I talk about this kind of Lagrangian,
take the real locus.
Yes, that's a real locus, and it has the think of going around with your one-Lagrangian transformation. That's kind of if I do something here in this total space, it's built in. I think the trick is I'm not working with dimension 2 here. I mean with the elliptic curve, but with a bigger space that involves this one-Lagrangian transformation.
So something like a Lagrangian manifold is some fixed point of
Yeah. Yes. Yes.
So the point is that here, Lagrangian is actually supposed to change. Because
What was this?
Wait, that Lagrangian and it's
no, there's no twist here. That Lagrangian by itself is supposed to generate a chemical.
the rectangle.
Yes.
Because under mirror symmetry, you're actually in an affine
Yes,
situation.
I understand.
And so you get
The structure
you
should
get
be
the
something.
structure sheet. So it allows you to, instead of considering, usually when you think of the elliptical, you have to consider the real locus and other twists. But this gives you a single Lagrangian, which is actually a fixed point set to the field. And then it should be enough to.
So if you have several Lagrangian, this corresponds to this different Hamiltonian and time product. You just consider one Lagrangian.
Yeah, but that's only one Lagrangian, exactly. But note that, right, I mean, otherwise we would, I can produce more Lagrangian sections, that's no problem in allowing some kind of like a universal thing. I mean, I would have a high dimensional parameter space. That would work, but no.
But ultimately, instead of talking about the replica of this total space, you're trying to go back to the category of the general fiber, right?
Oh, sure.
So
Yes.
somehow you're saying here that, by looking at this one Lagrangian, a particular orbit is some morphism, should be some morphism, maybe the
Exactly.
intersection with the fiber
Exactly.
and its monodermeter.
Yes. Yes. I mean, there are tons of challenges on the symplectic side here. To relate these red Foucault category to this category of the general fiber and all these things and how this relates to symplectic cohomology.
So another question is, my understanding is symplectic cohomology of an infinity structure rather than an infinity structure.
Looks, but it has an A infinity structure, just like quantum.
Right. So I know. Yeah, quantum cohomology has an infinity structure, but that's a kind of hard structure to understand.
It's kind of weird. It's E2 as well.
Yeah, just like relative function. So again, this is a very special case where you know your mirror is an affine line, and you know that the rapid cohomology for the computing is just rings of functions.
So I shouldn't worry.
So of course it's good that it's going to be mirrors because that's what you're doing it. So I mean,
Any other questions?
One more thing. So just at the beginning, I said that if you go to the downstairs, if you go suggest linear when someone called, if most flow is curved, and that's after I saw your pictures, you see that you got one dimensional ball up, and you have this straight thing, and you push down. Probably if you go down to something curved, right?
Something curved?
So you have this kind of. So that's pictures.
Yeah.
some kind of cone type thing, right?
right?
You have a straight line here.
Yes.
So you have kind of project down to this original dimensional state. I mean, this is
It's not curved, no, it's always a straight line. That's I mean, okay, the projection is not affine, yeah, but lines get mapped to
No,
lines.
but this says that you can do acceleration, right?
Yeah,
So you have two directions. The speed of acceleration in this direction and in this direction is different. This means that you have some curve. Then kind of this part is kind of more accelerated than this part. So
but we never do that. I mean, on any, whenever you move off, I mean, there's always a constant d associated to it. And the rule is that if
But
you go,
this is one
sorry, not
dimension
here.
picture, right?
No, but even higher dimension, it doesn't matter. You don't get curved, no.
I mean, this is to do with the fact that the Lagrangian is the graph of
Yes,
the function that
Exactly.
realizes.
the Lagrangian, I mean, Lagrangian is almost a misnomer, okay? So there's this confusing thing that in a way we work on the wrong side. So these pictures live in the tangent bundle of B, not in the cotangent bundle. Okay, and the tangent bundle has these natural Lagrangians which is like the graph of the developing map. The map that measures the distance or multiple of the distance. And if you take anything that is that measures, I mean, these kind of polygons span between these things, they will be straight. They will be tropical pictures of the things. I think what you're worrying about is so they could look like this, right? That's a picture that you would draw in higher dimensions. So it's made up of triangles and these kind of, maybe also some bigger things here, something like this, yeah. That's a picture, but any of these project to something straight. That's a picture of the fibers.
In the cotangent bundle it became curved.
The cotangent bundle would be curved, yeah.
That's
It's because it's tropicalized. I don't know why there's this magic thing and makes the cotangent bundle look like a tangent bundle.
So it's time to break again.